Thank you. Hello. Have you enjoyed the morning talks? They were excellent in quality. Yeah, it was excellent. Thank you. Let me start with a question, I guess. What would you do if you were given a machine that had, the power's on, clearly it wants to boot, it turns on, something shows up on the screen or the serial port, whatever, but that's all it does. And then you open it up and look inside and there's a processor that you don't recognize. You Google for that processor and, you find out that it did make it into production. It was popular for several years and then it got replaced. And you Google some more and you find out that GCC dropped that support 10 years ago. And there is no LLVM for it, and there's nothing else. It doesn't, it's an unusual processor. And you don't have boot media, and there's only like 4 other people that you can tell that have this machine, and none of them have boot media, and everyone's looking around for boot media, install media, copy of the drive, anything like that. So that was my situation. And yeah. So yeah, and that's the beginning of my story here. So today I'm going to cover for those who haven't seen Ghidra, which is a reverse engineering tool. I'm going to sort of do a demo of it, show some capabilities, explain why it's neat, and then spend the rest of the time talking about what was involved in teaching Ghidra. How to disassemble a new CPU. So that's the plan. Here it goes. So my machine that I was mentioning about, it's Tektronix. It wasn't given to me. I actually paid for it on eBay, but it was a steal, and I've been looking for one for many years. I've been enthusiastic about the Motorola 88,000 processor for many years, about 20 more maybe. Since about the time I was in college, I guess. And I have a number of them. Some of them do boot. Some of them run OpenBSD. And OpenBSD is one of the few open source operating systems that actually is supported for some of these Motorola 88,000 processors still today. So the Tektronix made a product called XD88. This was in the time frame when they were still making Unix workstations. They were successful somewhat with the 68030, 020, and 68K based machines in the 80s. And towards the end of that run, in about 89, they announced a high-end graphical workstation, sort of purposed machines called the XD88. Subsequently, they shipped for about a year or two, and then they discontinued. In fact, they actually sold off the entire division that did Unix workstations. And I think part of it went to the part that did X terminals, which were a thing back then, went to NCD maybe, and then I don't know where the rest went. So anyway, so that's a little background about the XD88, and I do have one that I'm showing at the exhibit tomorrow and Sunday. You can come take a look at that. I'll open it up for you. It doesn't do much other than it'll drop to the monitor and it also actually refuses to boot because, mine, I don't have the keyboard for it, and Tektronix made it in such a way that the machine wouldn't do anything until it recognized the keyboard. So I was going to write, yes. So I was going to write I thought about writing a disassemble. So I dumped the ROMs, so that was easy. It's a 32-bit machine, so there's 4 ROMs, and I had to, put them back together. That was easy too. And then I started disassembling by hand just to see if, the ROM was, in fact, instructions. And yes, it was. The first instruction, I guess, the first address was the vector to jump to, and it was a jump instruction, so that worked out fine. So I went a couple more, there's a couple loads and stores, and yeah, it all looked like instructions. But then immediately I got tired of hand disassembling stuff. It was good exercise in sort of learning the instruction set. But I was going to write a disassembler. I've done that before. But this time I heard about this tool called Ghidra, and I knew it was extensible, so I went to look into what it would take to describe the new processor. Anyway, so a little bit about Ghidra. It is an open source, professional open source tool, a professional reverse engineering tool, open sourced by NSA. And it was, I guess, open sourced 5 years ago, approximately in March. And it's been very exciting since then. But turns out, I did a little research, and apparently it's been going for 20-some years. Like year 2000 was the first time they started that. And it's a framework. It was proposed and built for the purpose of doing research on executables, binary code, for all kinds of different purposes. And it has a lot of features, and it is ground up designed to be extensible. So that's very attractive. So some of the features, of course, you come to expect from a disassembler today, that it can disassemble binaries of all kinds of different CPUs. It supports patching. Today, it supports emulation, which is a new feature that they added about 1.5 years ago. In the most recent release that came out earlier this year, they have this new thing called bsim, which is a feature for comparing binary similarities, where it sort of vectorizes the code segment and makes it similar across different things that you're comparing. And long story short, it will make finding similar code much faster. And they also have an architecture where you can, if you have a large amount of code that you want to search against, you can sort of put that into Elasticsearch, and there's mechanisms to make it work together. Okay, so it's a Java app, so it'll run on Linux, Mac, and Windows. And yeah, it's getting regular updates. There's a lot of new stuff that's pretty neat. Okay, yes. Oh, and here's the list of processors that it supports. Obviously, the Intel x86, the ARM 64-bit, PowerPC, MIPS, and all the variations, I guess. 68K, Motorola, Java, and DEX bytecoded would be the Android binaries. PA RISC, and PIC microprocessors, Sparks. I don't know what the CR16C is, but the Z80, 6502, 8051 is 8 bits. And I think you could, use the Z80 language to disassemble the 8080 stuff. MSP 430, so on and so forth. I guess there is no IBM Z series here. I thought there might have been, but okay. So there you go. That's the list. And this is where I'm going to switch to the demo mode. I'm going to skip all about all the install and stuff like that. That's pretty straightforward. You just follow the instructions. I'm going to start here. This is there's a notion of a project, and you have to create a project and stick binaries into it before you can do anything with it. And this is called the front end. In this case, I have a copy of the ROM that I stuck in here. These are the icons of the tools that you can start. You can actually have multiple of these running at the same time, but nonetheless, thing you'll do is go to File, Import Binary. You're going to select a file, I guess. Can I do it like that? No. I had to change the resolution so I can now get to. Some of the buttons don't show correctly, but anyway, so in the language selection, you're going to select all these languages. You can, of course, search for it, and I'm going to search for 88K. There's my processor definition listed here. This will not be in the normal distribution. You'd have to once you download the distribution, you have to copy the directory from wherever you're getting that language definition and drop it into the Ghidra processors directory, and then it'll show up in this list. So, there you go. So that's the part that I wanted to show there. And once you do that, it'll show up in the project, and it will have some properties. The Ghidra is really good about understanding lots of different file formats. So it'll understand zip file, it'll understand, obviously, raw binary, it'll understand ELF and COF and all the other PE for Windows executables. And basically, there's a lot of support for file formats. So that's covered there. In this case, I just, it was a ROM, so I selected raw. There is here about program. This will show some of the things that I selected about it. So it'll tell, I don't know why that's that, but it'll say how big the binary is and so on and so forth. Okay, so now I need to do this goofy thing to get to this. All right, anyway, so let's hop on to double-clicking on it. We'll start the tool. And you know, it's a reverse engineering tool, so you really want to do this on a really large screen with comfortable viewing, and it does start up in multiple panes, like an IDE of sorts. I've closed all the other windows so I can talk about each of the windows. In fact, actually, I want to talk about the binary window first. So, yeah, and you can get to all the windows from this menu here, and there's lots of things, and I'll cover some of these at least to. Okay. And by the way, who here is here for the Ghidra aspect versus who's interested in the learning about the processor definition part? Both? Okay. All right. Who's never seen Ghidra before? I see. Excellent. Okay. It's a very cool piece of tool, and I'm hoping that I can show you enough so that that'll stick in your mind that next time you have to disassemble something, that this will be a tool that you can reach for, and that it's worth investing a little bit of time into. Like any other tool, you do have to invest a little bit of time. Anyway, look, I'm going to start with this window, which is the binary window, and you know, it makes most sense. So this is my address here, and you can see there's some blocks that have FF, and there's some stuff at the end, and there should be some strings. Yeah, so there's some strings, and so on. Okay. Actually, yeah, so that's the binary window, and depending on the mode, you could actually click on that and start editing. If you do click on anywhere in here, it will actually take you to, on the other window, it will take you to, and I don't have the other window up. Oh, yes, I do, code browser. It will take you to, let me close that. It should take you to that, wait, what happened? I closed the wrong window. Oh, no. Interesting. Okay. I don't know what happened. Let's do that again. I'm looking for Windows that's called the listing window. Oh, no. Yeah, I know. Yeah, do I want to go back and change that, or this listing? Do you see listing here? I don't see listing. Okay. Huh. Let me try one more thing. Okay. I'm gonna. That's one, and that's the other one. I think I'm gonna try to close this. Let's try don't save. And all right, close enough. Okay, so this is the listing view. I'm sorry, I'm a little Okay, the listing view, and I actually wanted to turn off one of the fields to start with. I'm going to disable that so that I can explain a little bit. Actually, you know what? Is it in here? Yeah, okay. That's what I meant to do. Okay, cool. All right, I got lost. Excuse me for a second. This is where I need to go first. Apologize. All right, so I'm going to do the memory window, which not that. It's on the toolbar. So that little card-looking thing is the memory window. So in a disassembler, you're looking at a piece of binary, but you actually need to give it a little more context for the tool to figure out what it's looking at. And one of the things you can do is you can map a piece of file into a certain part of the memory, and you can also give it properties. So most likely, in the case of a ROM, this is only because I imported the raw binary. If you import a ELF file or a PE file, it will do the right thing for you. So you don't have to worry about this. But I'm just here to show you that you can do what you expect to be able to do, which is to have a section that has different starting addresses. So this is the ROM itself. It's a, what did I say it was? That's bigger than I thought it was. 64 times 3, 256K maybe? And these are some IO addresses that I've discovered. And this is the ROM high. So what? Yeah, not sure IOs. Yeah, so you're gonna you're gonna be disassembling and you don't know what it is. You know it's some kind of address, and so yeah, that was my convention. ROM high is that the ROM actually, after it's running for a little bit, it's mapped several places into memory, and it actually jumps to the same location that it was, except in the higher address. So it's exactly the same code that it's executing, but at a different address. This could be sort of a side effect of the memory management, where this is either cached or not cached or something like that. Okay. All right, so that's the memory window, and you can add and subtract and do stuff with this. I just wanted to show you that that's part of the tool. And then I show you the binary window, and then we have the, this is the listing view. And a lot of this is configurable. Each of these windows are configurable in terms of the font, the style, the coloring. There's also dark mode, which I don't use, but you can select that. That's a recent feature, I guess. Double-clicking on a label, over a label, will actually show you what might be at the other location. You can scroll through this. It's kind of convenient. Double-clicking will actually jump you to that location. That's interesting. Okay. And then over here is the address locations that actually reference this. So somebody else actually jumps to, oh, wait a minute, what happened here? I hover over this and it says, it's actually a pointer in ROM that points to this address. Interesting. So you can do that. You can, when you come to a label, you can rename a label. Of course, you're going to want to do that because you discover something, and this is going to be the do that thing method or function or whatever you want to call it at this point. So you can rename with that. And then everywhere else, the reference will, of course, change to that. So as expected from a disassembler. So that's cool. You can, if you think that some of these things are not supposed to be a hex character, but you rather see it in decimal, you can actually change. I did not think about this. There, yeah, there's a part of the menu that I can't select. Okay, well, the point is that you can actually tell it that it is whatever it is format that you want to see it, whether it be character or decimal or binary, I think. You could choose from those things. You can, what else can you do here? Yes, so you could actually run across some code. Here, this obviously is a string, and you could actually tell it this data is a terminated C string, and then it will actually change it to that. You can do that sort of stuff. Actually, I forgot to show you another window. There's actually a strings window, define strings, and from here, you can actually work your way back to find, what is this string used for kind of situation. You can search for it, and by the way, because I have the ROM mapped in two places, it actually has the low version and the high version too. And most of it, I think, I should be looking in the high version here. And like I said, any window, if you click on something, it typically jumps you to that other place. So that helps stuff. Okay, so that was that window. Let me make sure I'm not forgetting anything. The main window. Yep. And then the decompile window. Okay, so back to the main window. I'm going to close the strings and back to this. And I need to find some code. And by the way, over here on the right, it shows entropy. So you can see if a chunk of, it shows a lot of different things actually. So some of it's an errors, some of it is entropy, and some of it is, well, obviously there's where you are, some of it's what's highlighted, and anyway, so there's a bunch of useful things there. Okay, so here we are in a function. It figured out that, so it's pretty clever about these things. So R31, you know what? I think I forgot to, there's a slide about, a little bit about the Motorola 88,000 processor that I think you're going to, so briefly about the Motorola 88,000, that might be helpful for you to know right now, is that it's a 32-bit processor. It chronologically, it followed the 88,000, whereas the 88,000 was a CISC processor. The 68,000 was a CISC processor. The 88,000 is a RISC processor. This was Motorola's first production RISC processor. And then they were reasonably happy with it, but for other political reasons and other partnership deals, they then switched to the PowerPC line following this. Anyway, RISC, so it's all the instructions are very symmetrical. There are 32 registers, R0 through R31. R0 is constantly 0, and basically every register can be in an operand. And by the way, this one is what am I storing? So, and the leftmost, so in this case, it's a SD for store. The first operand is the destination. So we're storing into R1 we're storing R1 into the memory location contained in R31 plus 2C, and I guess I could rename that to a different, but the first instruction was subtract from R31, and R31 by convention was the stack, is the stack. So I'm decrementing the stack, and this is sort of what the Ghidra actually knows enough about the processor to know that when I do that, it's usually at the beginning of a subroutine or a function. So, all right, so that's what's going on here. And I've covered that. Good. Okay, so now I'm going to show you another window, which is called the function, first of all, the function call trees, which is kind of a useful window. So if you're in a function, you're likely going to be called by somebody else, and you're likely going to be calling something else. And so this is what that shows. There's the incoming references versus the outgoing references, and you can sort of drill down and go to, for example, this one appears that if I double click on it, no. Why does it not jump to it? Looks like there are no nodes underneath it, so it could be a good target for me to disassemble, start here. Anyway, so that's the function call tree, and that's really handy. And then there's another view called the function graph. Is that this one? No, symbol tree. Okay, symbols are important too, although these, symbols can come from a number of different places, depending on what you're analyzing and your context. So if you're analyzing an ELF file or other file formats that have the debug information in it, the symbols, it will actually list here. So depending on what you're linking, the actual function names will show up here. If you don't, sometimes, depending on the community and the kind of things you're disassembling and the file format, the community sometimes supplies a file that you can load for that purpose of disassembling whatever it is that you're disassembling. And the ones that Ghidra finds and the stuff that U-labeled will show up here, in my case, like so. And then you can jump through the symbols. There's also types, so it not only does it know symbols, but it also knows about types, and there's, again, lots of different ways to import the types. You can actually parse a C header file. You can get the type information from libraries and other places. So that's handy, and that would be it. In my case, I don't have much to show, but there's a window called Type, Data Type Manager. So there you go. And I don't think I have any types here other than the defaults. So that's that. Okay, let me get rid of that. Okay, so one more thing on this screen that I wanted to show, and like I said, lots of things are configurable, and one of them is the fields, and there's one field here that I disabled initially. I'm going to enable it now. It's called the Pcode. In reverse engineering, in Ghidra, I didn't mean to do that. Let's see if I can recover. I need to do that. Okay. All right. In Ghidra, two things are going on. One is the disassembly, which is to say, when I see this binary here, 1C49000, and by the way, I didn't mention it, but every instruction in this processor is 4 bytes, and everything's 4-byte aligned, which does make the job of the disassembler a little bit easier. In this case, and Motorola syntax is such that .b is indicative of a byte, so that's the size of the operation. LD is load, and in this case, it figured out, I guess I must have named this, it must have figured it out, or I must have named or told it that the function here takes parameter in R2. I think this is one of the things that I did, but where was I? Okay, here it is. I turned on the Pcode, and the Pcode is a lot of jazz, and it's a lot of stuff. And what this is actually the semantic behavior of that instruction. So part of defining the CPU for the processor involves telling it how to produce the assembly code, as well as the arguments, as well as describing what the instruction actually does. And in this particular case, it adds the quantity 0 to R9, and it pulls the contents from RAM, and in this case, it sign extends it to the size of 1. So that's what this instruction does. And Ghidra knows about it, and it uses this to then do what's called decompile, which is more than disassembly. The disassembly really finished when we displayed this. And the disassembly alone was quite helpful. So with that, I'm able to look through the source code and see what's going on in the ROM, and that was that's very helpful. The decompile, there is a decompile window here. If I find it, here it is. The decompile actually tries to make C-looking code out of the assembly, and it could do that to varying degrees of success depending on how accurate your semantic definition is. So if you get that semantic definition perfect, which the languages that come with the distribution, they're top notch, and it'll produce code that looks like real C code, and or whatever it is that will take for you to figure out. My semantic definition is partial. I did the best I could so far up to this point, and so the decompile output is not perfect, but it is useful enough for me. So that's one of the things that Ghidra offers. And so if you're decompiling an existing processor, you'll have really good, you'll be quite happy with the output in this window here. Okay, so that's cool. The other thing that it does is that search. So search is quite good, and you can search lots of different things in lots of different ways. And so you can, first, obviously, you can search memory for patterns. You can specify regular expression over that hex, over the binary hex values, I guess. I don't do that often. Typically what I do is I search for the last 4 digits and I get what I'm usually looking for. What just happened here? I must have clicked something else. I guess I clicked that. Okay. All right. And then you can also search for, let's see, you can search for text. You can search for text in different places. So you can search, I didn't show you the comments, but you can search comments, you can search labels, and you can search the mnemonics or the operands or all of the above, that sort of thing. That's kind of handy. A comment would be a really nice thing for me to show. So there's lots of different ways to add comments, but basically when you add a comment, it'll stay there, and when you come back, it'll be there. You can also output it to the, if you are producing a .asm file, you can output it to that. So different kinds of comments. There's end of line comment, which is basically this value means something or else. There's a plate comment which happens in above the functions. There are post comments, and then post is after, and pre is before. This is a plate comment, for example. So that's what a plate comment looks like. If I have a constant, I could sort of describe the constant. So, comments. All right, did I cover everything else? No. The graph window, I forgot about the graph window. Okay, so I was going to go to the graph window and I got distracted with the symbol tree. The graph window is this one, there you go. Okay, so the graph is basically a visual sort of helper for how these code segments connect together. And it's basically the data flow or the relationship of can it call this, can it call this. Each block is basically a chunk of instructions that will never be interrupted or broken. And if it knows there's something jumping into it, it will actually split that into 2 separate blocks. So that's the sort of idea behind it. This is helpful in visualizing, the function that you're trying to figure out. Okay, and then there is another one called the function. There's a window. There's another graph called what's it called? I can't remember the name. The call graph. Call trees, I guess. And that's the call trees. I'm sorry. The call graph basically shows you this function calls that, and it's called by this other one. So if you double click on this, it'll show you that and that sort of thing. Go back here. Sometimes this is helpful. Okay, so that's the graph window. And we did the search and the export and other features. Okay, so I talked about the search, and then you can do, what am I trying to say? You can export. So yeah, once you disassemble, you may want to have a .asm file, or you want to try to reassemble it to see if your disassembly is correct. And you can then export lots of different things. And one of the things is like text file that you can export from here, and with options. So that's the basic features. In addition to this, the things that I didn't mention, the patching support would be like, you want to, instead of calling a function, you want to basically call your stuff first before you're calling that, and it'll help you do that. It knows how to compare binaries across multiple versions. So if you say these 2 programs are related, this one comes first and this one comes next, it will actually do a diff, and gather all the stuff that's the same and sort of show you in a diff format the things that are different. There is you can start the project. Each project, when you create the project, it asks you, is this a shared or a not shared project? If you have a Ghidra, you need a server to support this, but if you know the URL to the server, you can actually have a collaborative disassembly workflow enabled. That will enable basically your work is visible by other people and you can see other people's work. And I understand that there are some gaming communities where people reverse engineer the game and share do that in a collaborative fashion. So this is something that I'd like to try soon. And then scripting, everything can be scripted. So whatever you do to that binary file, you can basically write it up into a script. You can script it either from Python or from Java, or I guess maybe there's another API. And you can basically apply that to a whole directory full of binaries, if that's what you want to do. Or there are lots of community-generated scripts that will basically, depending on what your task is, you can go and run a script. And I'll show you running a script in just a little bit, because there's a task related to defining processors that you can do that. And of course, you can run this without the GUI. So again, if you have a script that does lots of things to a directory full of executables, you don't need the GUI, and you can basically run it from the command line. So that was the demo part of it, and I think I'm going way longer on that. I was kind of afraid of that, but kind of also knew that was going to happen. Anybody at this point have any burning questions or? Okay, good. I'm going to move on to the next part, which is the defining the processor. At a high level, there's a domain-specific language called SLAY, and you're going to do most of the specifying the processor in this language. And I'll sort of step you through some of that and maybe show you some examples. Hopefully, it'll be illustrative. But long story short, it's for getting to the disassemble, to accurate disassembly, it's doable. It's not too convoluted. The documentation's not terrible. There's community and examples and blog posts and stuff like that to help you out. So that part's doable. Of course, you are doing this for a processor that has instructions, and you're going to have to do for each instruction. So there's a little bit of a grind that you can expect. What I found out is that for the ROM code, and I can tell that ROM code was hand-assembled versus the C compiler-generated ROM code. And for the hand-assembled stuff, there's actually even fewer instructions that you actually need to sort of encode, because you don't use all the instructions. Similarly for, I guess, the C compile output, that the code generator only uses so many patterns from the instructions. So what I found is that the 80-20 rule sort of applies, in that, I sort of started from the top and did, the first day was a lot of instructions, but after several days, I got to the point where I could read the disassembly all day long and not encounter a sort of an illegal instruction. When I went into one of those, I'd basically try to describe it and move on, but they get less and less frequent pretty quickly. So that I can say is very doable. The semantic definition part is a little bit of a pain, and getting it right takes considerable effort. It's sort of like programming, but yeah. And validating it is even harder. So that's sort of the takeaway, I guess. So let's define a process. So again, we are generating a data structure that's going to feed into a disassembler, and disassembler, largely what it's going to do is it's going to look at the instruction, the binary and the instructions, and try to match a instruction onto it. So at the end of the day, if you've done this, you'll probably know, but instructions are sort of grouped together. The encoding of the instruction is bits are grouped together for certain meanings. And so this is an example here for these 4 arithmetic instructions for the 88,000. And this is all 32 bits. There is basically the first 6 bits here sort of describe the arithmetic instruction. And then the differences occur around here. D is 5 bits worth of the destination register. S1 is the source register, the first source register, and here's another, S2 is another source register. And if you add these all up together, there's 32 bits. So that's, and every instruction, every manual, user guide, user manual for the processor comes with a page like this. In fact, typically there is in the back of the manual, there's instructions sorted by the byte, the first byte, and also by category like arithmetic and logical and stuff like that. All right, yeah, so this is the page that I had in mind earlier, but it's 4 bytes for the fixed instruction set, and everything is 4 byte aligned, and 32 general purpose registers, a bunch of floating point registers that I haven't sort of had to deal with, and then a handful of control registers, and cache and MMU were external to this generation of the processor. So cache and MMU related stuff ended up being just sort of a write to a control register that actually was off die. And it's there's an instruction for storing into control registers and reading from control registers. Okay, so this is a sample. Well, this is the first part of the SLAY file that you'd come up with will look like this. We are defining a token, which is the interpretation of the instructions. And in this case, the token name is INST, and it's 32 bits wide. And for that token, there are these fields. Fields are the grouping of the bits. So I'm saying OP1 is bit 26 through 31, which is that leftmost. If we go back to this part, this I ended up naming OP1. This is going to be D, this is S, this is, not sure what I named it, but we'll find out. And so that's, and there's lots of these. These bit groupings called fields, they can overlap, and they just need to be unique. So this is like so depending on the instruction, you may care about this set of bits, whereas the next instruction you care a different set of bits. They might overlap, but you can define a name for that second set of bits as well. So and these I pulled these out because they're going to be used in the next part. All right. There's a notion called space. This is basically a contiguous address space. There needs to be at least one default space, and you're going to define properties about that. Typically, registers are placed into a space, and it's of type register space, and it looks like this. So, I'm only showing the first 32 general purpose registers here, but if it's a clever mechanism, but this allows you to also specify register pairs if you do register pairs depending on the machine, the processor. Okay, so I told the SLAY that I have registers, that many. And then there's this notion called attach. And attach variables is, so sometimes you have these 5 bits, for example, D, S1, S2, these are the 5 bits that I showed in the previous instruction. Those 5 bits, by default, a field is interpreted with as an unsigned integer. So you have 5 bits, and if it's 00001, that means integer 1. Sometimes those 5 bits you want to, in this particular case, D, S1, and S2 will always be interpreted as registers. So I can basically say, instead of those integer values, these are the registers that for these fields, this is your new interpretation called variable. So then wherever I use D, the result will come back as R something. So that's very convenient. Here's an instruction. Again, this is unsigned integer add. I may get this. This is sort of, I don't know if it's a RISC thing or if it's just a Motorola thing, but the CI, CO, CIO is basically what to do with the carry flag. And you can actually specify it for each time. The programmer has, the programmer describes what he wants to do for that instruction, whether to include the carry coming in or to produce a carry going out or to do both at the same time. And that's specified like so. And that, do I have it here? Yes, okay, good. And then note that there's two different modes here. One is called I can't remember the name of the mode, but it's the destination source 1, source 2, and the other one is destination source 1 with the immediate 16-bit immediate value. Okay, this is what the manual says. So for the register with 16-bit immediate, it's gonna, these are the bit patterns, and the triadic register mode, which is the 3 registers, the bit pattern is like this. Okay, and then destination register, source register, and these are the IO stand for the what to do with the carry, whether I produce one in or whether I take one in. Okay, this is what the actual SLAY language statement will look like. I picked this one because it's one of the simplest patterns. The actual instruction, for example, might be F5606000, and this sort of breaks down into add unsigned register 11 with register 0 and register 0, which actually is a silly example because adding 0 with 0 and storing it into register 11 is not that exciting. But for the illustration purposes, it does fine. There's a section called the display section, and this is concerned with the disassembly. This is like I said, there's two things going on in the processor definition. One's the disassembly part, and the other is the semantic definition. Oh, crap. This should actually not say display section. This should actually say semantic behavior right there. Okay, I apologize. Anyway, so the first part is the display section from the colon up to the is, and that's where it breaks. The next part is the bit pattern section, and this is where you specify the bits. And in this case, and actually I need to be more specific here, this is, because the line starts with the colon, this is basically a top-level constructor. That's the other term that they use for these lines. And top-level constructors are very special in that the first identifier-looking thing is not an identifier. It's actually parsed as a literal. So ADDU, that string is actually going to go going to the output of the disassembly result. The next is actually, from there on, identifier-looking things are actually identifiers, and in this particular case, it's sort of locally scoping them to, we're declaring that we're going to use D, S1, and S2. And here are the references there. In OP1, I'm specifying the bit pattern according to the manual, and OP11 is what I ended up calling it. There's 11 bits worth of stuff that uniquely define that instructions, and that pattern is per this right here. And that's assuming I and O are both 0. And then S2. And the only thing that's notable here is that at the end of the day, you need to specify all 32 bits. Yeah, all 32 bits need to be accounted for, I guess, not specified. So in this case, these are fixed bits. This is another fixed bit. These are actually not fixed. It could be anything that's 5 bits worth of stuff. So anything between 0 and 31, indicating register 0 through 31. And finally, the last part in the square bracket, this is the semantic definition. This is, again, a simple example. The result D, which is a register, will receive values, the sum of S1 and S2. Okay, I think that's all I need to say about this slide, other than, again, the correction, that's not display, that should be something else. All right, so that's fine, but it's actually, that's not enough to do, that's enough to do like 75% of the stuff there, and then they get into a little more complicated stuff. Here's another example here, and this example is here because it uses the next part. bb0.n, in case, is a, what is it? Branch on bit being 0 instruction. The .n is a notation for RISC processors, I think, typically, in that it specifies that the branch delay slot is going to be used. And the branch delay slot is the instruction that follows the branch because of how the pipeline, instruction pipeline works. By the time you execute the jump, the next instruction has already been decoded and ready to go, and you could use that, or you can, if you don't use it, then you just throw away the result, and it's a little bit wasted. So that using the branch delay slot was one of the optimizations that you could choose to do. Anyway, so .n is that, and Ghidra actually has support for that, and it's here. It's a predefined semantic behavior function call-like thing, and that just says in this, if I have a .n, then that means insert the delay slot here and do the right thing. Okay, but the part that I wanted to show here is that the dest16 here is actually a little bit, it's a nested construct, and that was defined in several lines above, like so. The colon is not at the beginning of the line, so this is not a top level, and this ends up being a table entry with the table name of dest16. And still, the display part is up to the is, so rel, whatever rel is. And by the way, this, because it's not a top level, this is not the mnemonic. This is going to be interpreted as an identifier, and basically it's computed right here in this square bracket, which is another section called, what is it? Disassembly action section. And it's used, this is sort of one of the examples that they use, which is if you're doing relative branching and you need to compute the branch target, this is how you specify it right here. I am saying sim16, which is, I'm referencing sim16. sim16 was defined in the fields as, it's exactly the same bits from 0 to 6. Ooh, right. All right, so the long story short, the important part here is that you can basically nest these constructs and build them up, and that's very helpful. And I think I talked about the semantic behavior. I could show, by the way, the QR code links to the slides. If you're actually doing this, you can reference the slides here. The one thing that I wanted to show here, and then I can wrap it up, is that there's a bunch of scripts that it comes with, and one of the scripts is slay. Under slay, there is the debug slay instruction, so it actually prints debug information about your slay definition, which is useful, and reload slay language. So I use VS Code. I'm typing along. When I'm done with that, I hop over here and I basically select the script, I run the script, and it'll reload the language. If there's a syntax error, it's a little cryptic about it, but you can find it in the console, the other console, about what you did wrong in that definition, and that should fix everything there. I think that's the end of my presentation. Yeah, that's the debug stuff. I have some tips in there too if you're interested. I'm probably going to create a starter repo that has basically the smallest thing that you need to get started with, and I'll put all the tips and other stuff in there. That's at least the plan. So if you're interested in that, reach out to me. And here's some more tips. I didn't talk about these files, but you can read about them online. I know I'm running out of time, so that's it. Thank you very much.
Do we have any really quick questions for Maki before he goes? I have one question. Can you, so if you wanted to apply this to an old system, like the old 1130 or something like that,
Right.
would you be able to also supply something that defines how the object code looks?
Yes, so I did look into this. One of the current limitations is that the on-disk representation is byte, can be
Okay.
broken up into bytes or padded to bytes, I guess. So if you have like a 12-bit instruction set, so long as they're like on disk, 16 bytes at a time, then you can probably make it work.
All right. Thank you very much, everybody. Give it up for Maki Kato.